All right, guys. Welcome to your business calculus lesson 4.4 on extrema and concavity. As usual, Daisy, Scout, and I are here to present your lesson. So let's clarify some terminology. Critical numbers. Let f be defined at c if f prime of c is 0, or if f is not differentiable at c, it's undefined at f prime of c, or it's undefined at f of c. Then C is a critical number of F. We call F of C a local maximum, like this one right here, if there exists an open interval M to N containing C such that F of X is less than C for all values from M to N. We call F of C a local minimum if there exists an open minimum, an open interval M to N containing C such that f of x is greater than or equal to f of c for all x values between M and N. Relative or local extrema occur only at critical values. Now, there's also absolute extrema. If f of c is greater than or equal to f of x for all x in the domain of f, then f of c is the absolute maximum of f. If f of c is less than or equal to f of x for all x in the domain of f, then f of c is an absolute minimum of f. So let's look at the extreme value theorem. A function f that is continuous on a closed interval from a to b has both an absolute maximum and an absolute minimum on that interval. And they must occur at the critical numbers we talked about before or at the endpoints. Okay, so let's kind of look at it. If f is continuous over a closed interval, then f has a maximum and minimum value over that interval. So here's an example of where the maximum and minimum occur at interior points, at critical points that are not the endpoints. Here's one where the maximum and minimum occur at the endpoints. And here's one that's kind of mixed. We've got a maximum at a critical point here on the interior and a minimum at an endpoint. So the difference between local maximums and absolute maximums are that a local maximum is just the maximum in it, like its little neighborhood. And then the absolute maximum is the maximum in its neighborhood, but it's the maximum function value for all the x values in the domain. The local minimum is a minimum in just its little neighborhood, but the absolute minimum is not only a minimum in its neighborhood, but for the whole entire function. Local extremes are also called relative extremes. Notice that local extremes in the interior of the function occur where the derivative is 0 or the derivative is undefined. Okay, so we want to find the absolute maximum and minimum values of f of x equals x to the 2/3 on the closed interval -2 to 3. So the first thing we need to do are find the critical points. So we need to find the first derivative of our function. So we apply the power rule, and so we're going to have 2/3 x to the -1/3 because 2/3 minus 1 is -1/3. And let's rewrite that in radical notation. So we have 2 over 3 times the cube root of x. Okay, so there's no values where we're going to make that equal to 0, but the first derivative is undefined at x equals 0, so that fits our criteria for being a critical point. So 0, 0 is indeed a critical point. Because the function is defined over a closed interval, we must also check the endpoints to see if they contain the absolute maximum or absolute minimum. Okay, so at x equals 0, the function equals 0. So that comes from our critical point. In order to determine whether we think it is a maximum or a minimum, we need to check values of from both sides of it that don't go all the way to our next critical point. So we're going to try f of -1, and that equals 1, and f of 1 also equals 1. So 0 is less than 1. So it must be a local minimum and possibly a global minimum. We won't know if it's the global minimum until we check the function value at both endpoints. So at x equals -2, our function is equal to -2 to the 2/3 power, which is going to be 1.5874. At x equals 3, 3 to the 2/3 power is 2.08008. And so we can look and see that 0 is less than both of those, so that's going to be our absolute minimum. And then the largest value we have is 2.08008, and so that's going to be our absolute maximum, and we'll just round to a hundredths place there. Okay, so finding maximums and minimums analytically, you find the derivative of the function and determine whether the derivative is 0 or undefined. These are the critical points. We're going to find the value of the function at each critical point. Then you're going to find the values or slopes for points between the critical points to determine if they are maximums or minimums. And for closed intervals, we'll check the endpoints as well. Okay, critical points are not always extremes. Okay, so right here at y equals x cubed, the first derivative would be y prime or f prime equals 3x squared, and so that's going to equal 0 at 0. So right here, here's a case where the critical point is not an extreme. It's not a maximum or a minimum, either one. If we were to find a function value to the left, it would be negative, and the function value to the right would be positive. So that indicates that if there's a sign change like that, that means that you have neither a maximum or minimum. That's one way. That works when you're at 0. Other cases, you'll have to look. It'll be less than your function value for that particular x value, and then moving to the right, say you'd have an x value that produces a function value that's greater than the function value produced at your critical point. Here's another case. Y equals x to the 1/3. The first derivative of that would be 1/3 x to the -2/3. So at x equals 0, that's going to be undefined. And so again, here's a case of a critical point that's not a local maximum or nor a local minimum. So critical values are not always extremes. They are just candidates to be extremes. Okay, guys, that's it. Go ahead and print out your problem set and see what you can do. We'll work on more problems together in class. I look forward to seeing you. You know where to find me if you have any burning questions. Thank you so much for watching the video.